the universe undoubtedly extended, empowering out and out more. First-rate length after this period, it persevered to develop, however, at a more languid expense. In the changing over into the universe we concentrate on as of late, that is the inflationary hypothesis of the collectible cosmic impact, the most prominent and generally saw speculation of how the universe began. Anyway, for a couple of physicists, this head theory does no longer precisely painting the develop of our universe. Com.ed. The universe existed before that thing, stretching out endlessly into the past as well as into the future. Even as the universe is expanding these days, it became contracting ahead of time than the enormous detonation. In this view, the enormous detonation isn't really a bang, as a jump, a second even, while the contracting universe exchanged ways and headed out to make once more. As laid out through their hypothesis, the universe might have to sidestep with preceded with improvement, dissuaded by a breakdown inside the some distance future, then another leap. A few physicists proposed the S may be endless. This horrible circumstance, the standard cosmological view in which the entire matter originated with a huge bang, is also difficult circumstances. The hypothesis of how things arrive to advance, that something can't rise out of nothing, adding to the stress. The James Webb Telescope has made alarming disclosures conflicting with the idea that the enormous detonation might be thought about the start of the universe. These discoveries convey up the inquiry. If the huge explosion wasn't the start of the universe, then what was? Should the universe in the long run start with a detour or something most certainly unmistakable? The idea that the universe had a start, or an evening with no yesterday as it became originally analyzed, gets back to George Lemaitre in 1927. Simultaneously, it's far a less than ideal circumstance to show that the universe probably had a start. That length of cost history has barely anything to do with the hot broad bang that portrayed our basic universe. However, exceptional area subject matter experts, or even a minority of experts, regardless of the reality that live with conviction that the enormous bang denotes the earliest reference point of all that matters, considered the definition is out of the enormous explosion. It isn't the introduction of life as we may be mindful of these days. In truth, there may be a ton of proof highlighted a non-singular start of our universe. We never showed up at these ends, dependent generally upon no prominent endo or over-the-top temperatures. Our universe is great characterized by means of an inflationary length that occurred previously the enormous explosion. The enormous detonation is the stop final result of what passed off inside the bearing of the culmination of progress. During improvement, the universe altered into most certainly void. No garbage independent of no F photons, just void region. Space itself became loaded with a gigantic amount of strength at each spot. This power changed after some time, reaching out in a rapid and resolved design because the universe delayed those adjustments, relaxed to monstrous augmentations. While new bound scale adjustments have been made to zenith, this superposition of insecurities all through scales is a portraying component of cosmological expansion. It's for inconsistent reasons, not purpose. If you lived in an expanding universe, you may potentially find close by locals where an expansion arrived at an end, or the region among you and them delayed persistently. In short, you could attempt to acquire what takes place nearer to the start of a huge effect before that area disappeared practically from view. It incorporates a little neighborhood local taking all things into account, probability no more prominent standard size than a human great hamster ball. Anyway, probably impressively bigger, the power capability of area then at that point gets changed over into be counted furthermore radiation. This change happens quickly, taking structure rapidly, yet not prompt because the energy shut up itself changes over into flume and some photons and more. The temperature rapidly expands from only a couple of degrees above outright zero to maybe around 20 Kelvin throughout the indistinguishable rapid time period due to the enormous level of energy adjusted. All that activity is near the speed of light. All particles go about as radiation with colossal strength, whether massless or gigantic antic. This change is called warming, denoting the finish of progress and furthermore the beginning of the degree alluded to as the new enormous bang. As progress continues, you'll witness a colossal substitute from all past circumstances. While the current enormous detonation starts, the expanding universe fast dials back after the secret picture of progress in an inflationary universe spot expands absolute illy with more prominent and expanded way regions strolling ceaselessly. Even as progress closes and the new enormous bang gets going and advanced, more farther areas will subside from you to an always developing certificate. It continuously as time advances, the piece of the universe in which improvement closes sees the augmentation cost drop, while the expanding regions surrounding it see no such drop under augmentation. The space to any object should double after a particular length, and while that equivalent measure of time slips by, that distance duplicates once more endlessly. Once the huge explosion begins, this alteration, since the expanding universe eases back down after the underlying second of improvement before the enormous detonation, you may experience improvement clearing off with adjoining regions. Those areas where in-improvement closures will load up with antimatter and radiation and make greater more slowly than the as-yet creating locals, leaving you in the expanding neighborhood as a standard organization within spacetime. Those areas in which intensity enormous bangs get uprise as far away from elite places where improvement keeps. Because of this, they'll expediently subside from one another's view within the standard inflationary picture. Because of this, the improvement charge changes. There may be a little gamble that any universes with separate warm huge bangs will of all time cooperate. The area where we come to live gets rather fortunate, and improvement arrives at an end for us. The power normal for space itself gets changed over to an intensity-dense and nearly uniform expanses of particles with the number 1 blemish and furthermore takeoffs from consistency concerning the quantum changes that existed and were relaxed. Across the universe, faster or later of advancement, the high-quality energy quantum fluctuations compare at first to overdense regions, while the awful energy fluctuations get converted into most importantly under regions. Those include as the seeds of huge structures we can't see. Those thickness fluctuations lately, as they had been even as the universe most importantly went by means of the intense broad bang, there are not any noticeable engravings we can get admission to from that early span. Subsequent to going through extra affiliations, in spite of the fact that we can extrapolate back to figure out the underlying thickness vacillations, tracking down something consistent with the story of cosmic improvement. The temperature vacillations are engraved inside the inestimable microwave record, CMB, presenting proof of how the enormous detonation began. Yet, there are different irregularities most of the CMB and our cutting-edge form of cosmology. We're missing something, and individuals can be summed up in 4 irregularities. First, on chiefly tremendous scales, the universe isn't generally acting as anticipated. The light from the CMB is being lensed by means of our Among Us, and the CMB that means the depend behaves like an enormous focal point, bending and changing over the plentifulness of the gentle in the return of it. The volume of this lensing isn't continuously predictable with our bleeding edge model, representing a high-quality mission for cosmology. Besides, the different sides of the equator of the CMB sky have unfeigned normal temperatures clashing with the assumption for consistency inside the universe's earliest degree. The possibility that the universe should have begun dependably results in various irregularities. Third, the expense of the Hubble constant, which depicts how fast the universe is expanding, changes contingent on whether we measure it from the astronomical microwave noteworthy past CMB or from neighboring stars. All in all, those abnormalities proposed we are inadequate with regards to something fundamental by the way we decide for the universe. One proposed arrangement comes from circle quantum cosmology, which starts from circle quantum gravity on the structure of life. In circle quantum cosmology, there's a littlest size of spot, the Board scale, or 1.0 times 10 to the power of -35. This approach implies the inner enormous bang couldn't exist in a universe depicted through this rule. As an alternative, the universe should by no means come to a limitlessly little dense issue near the huge explosion. In circle quantum cosmology, while the universe became tiny, quantum rectifications and anticipated a frightful strain causing a leap on the other hand of a peculiarity. This shows that our universe might have begun from a first universe that contracted after which broadened all over again, similar to a phoenix rising from the cinders. While the idea of an enormous skip isn't absolutely new, all the time circle quantum cosmology gives a numerical structure to help its cyclic time. Very much like the possibility of an enormous jump, it is moreover situated in H cosmology, including in a similar manner. To this thought, if circle quantum cosmology is right, the early universe may have had a gentle energy and thickness. This current circumstance ought to alter the CMB showing up as gentle varieties in temperature all through the sky. These varieties measured through the quality energy range offer enormous proof of the universe's foundation, further guiding the chance of a leap. Ordinary circle quantum cosmology offers a convincing and open door to the ultramodern huge explosion variant, possibly settling a portion of the drawn-out status irregularities in cosmology and providing bits of knowledge into the beginnings of the universe. It additionally shows the significance of should be prepared for one-of-a-kind 5 edges and able to say something the spirit to be fair and high-numbering. Concerning as we delve deeper into the mysteries of the cosmos and the theories that attempt to explain its origins and evolution, we encounter a rich tapestry of ideas and discoveries that challenge our understanding of the universe's beginnings. From the early formulations of the Big Bang Theory to contemporary advancements in cosmology and quantum physics, the quest to unravel the secrets of the cosmos has been a journey marked by profound insights and ongoing mysteries. The Big Bang Theory, which emerged in the early 20th century, represents a pivotal moment in our understanding of the universe's origin. It posits that the universe began as a singular point of infinite density and temperature approximately 13.8 billion years ago. This primordial state rapidly expanded in an event known as cosmic inflation, where space itself expanded faster than the speed of light. The inflationary period lasted for an infinitesimally brief moment, but its effects set the stage for the subsequent evolution of the universe. During inflation, quantum fluctuations in the fabric of spacetime were amplified to cosmic scales, seeding the formation of structures we observe today, such as galaxies and clusters of galaxies. These fluctuations left an imprint on the cosmic microwave background, CMB, radiation, which is now studied to understand the universe's early conditions. The discovery of the CMB in 1964 provided compelling evidence for the Big Bang Theory, as it offered a snapshot of the universe when it was just 380,000 years old, a mere blink of an eye compared to its current age. Following the inflationary epoch, the universe entered a phase dominated by the interaction of elementary particles and radiation. This era, known as the Hot Big Bang, saw the universe cool and expand further, allowing protons and neutrons to form within the first few minutes. These nucleons eventually combined to form the first atomic nuclei in a process known as Big Bang nucleosynthesis, which laid the foundation for the universe's chemical composition. As the universe continued to expand and cool, photons decoupled from matter, creating the cosmic microwave background radiation. This faint glow permeates the universe and provides crucial insights into its early history. Measurements of the CMB have revealed subtle temperature fluctuations, which correspond to density variations in the early universe. These fluctuations serve as the seeds from which galaxies and larger cosmic structures emerged through gravitational attraction over billions of years. While the Big Bang Theory has provided a robust framework for understanding the universe's expansion and early development, it also raises profound questions about what came before and what lies beyond the concept of cosmic inflation. For instance, inflationary cosmology posits that our observable universe is just a tiny patch of a much larger cosmos, possibly one among many in a multiverse. Inflationary cosmology suggests that rapid exponential expansion occurred not just once, but potentially multiple times, giving rise to an ensemble of universes with different physical properties. Moreover, advancements in theoretical physics, such as string theory and quantum cosmology, offer alternative perspectives on the universe's origins. String theory proposes that fundamental particles are not point-like objects but rather tiny vibrating strings of energy that exist in multiple dimensions beyond the familiar four of spacetime. This approach seeks to unify all known forces, including gravity, within a single theoretical framework. Although definitive experimental evidence remains elusive, quantum cosmology explores the application of quantum mechanics to the entire universe, including its birth and evolution. It suggests that the universe could have emerged from a quantum fluctuation or existed in a timeless state before experiencing a phase transition akin to a Big Bang event. These speculative ideas challenge traditional notions of causality and raise fundamental questions about the nature of existence itself. In recent decades, observational astronomy has provided unprecedented insights into the universe's structure and evolution. Advanced telescopes and observatories, such as the Hubble Space Telescope, the Atacama Large Millimeter/Submillimeter Array, ALMA, and the James Webb Space Telescope, JWST, have revolutionized our understanding of cosmic phenomena. These instruments have enabled astronomers to study galaxies, map the distribution of dark matter, and observe the afterglow of the Big Bang with unprecedented clarity. The study of dark matter and dark energy remains one of the most pressing challenges in modern cosmology. Dark matter, which constitutes about 27% of the universe's total energy density, is inferred from its gravitational effects on visible matter and light. It plays a crucial role in the formation and evolution of galaxies and larger cosmic structures, yet its precise nature remains elusive. Dark energy, comprising approximately 68% of the universe, is even more enigmatic. It is a mysterious force that permeates all of space and is responsible for the accelerated expansion of the universe. The discovery of dark energy in the late 1990s, through observations of distant supernovae, revolutionized cosmology, and led to the realization that the universe's expansion is not only continuing but accelerating over time. This finding challenged previous models of the universe's fate and underscored the need for new theoretical frameworks to account for its behavior on cosmic scales. One intriguing possibility is that dark energy may be related to modifications of Einstein's theory of gravity on cosmological scales, or to exotic forms of vacuum energy predicted by quantum field theory. These hypotheses represent active areas of research as scientists strive to understand the underlying physics driving the universe's accelerated expansion. In parallel, the study of gravitational waves has opened a new window onto the universe's dynamics and evolution. Gravitational waves are ripples in the fabric of spacetime caused by the acceleration of massive objects, such as colliding black holes or neutron stars. The direct detection of gravitational waves in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, marked a monumental achievement in astrophysics and confirmed a key prediction of Einstein's general theory of relativity. Gravitational wave astronomy promises to revolutionize our understanding of cosmic phenomena, offering unique insights into the mergers of black holes and neutron stars, the nature of extreme gravity, and the origins of heavy elements in the universe. Future observatories such as the Laser Interferometer Space Antenna, LISA, aim to detect gravitational waves from space, further expanding our observational capabilities and unlocking new discoveries.